Okay, thank you very much for being here. Today we have a guest, Giovanna Liberato. She did her study in Valongo Observatory and is currently doing the master there. And will be visiting us until the 22nd. Okay. So she will talk about planetary nebulae and stresses of galaxy evolution. So,
Thank you. So thank you for the opportunity, and thank you for being here. I'm very excited to be able to share a little bit of my master's project with you. So yeah, the title of the whole project is Planetary Nebulae as Traces of the Dynamical and Chemical Evolution of Nearby Spiral Galaxies. My advisors are Professors Denise Gonçalves and Ariana Cortez. Okay, so in this project, we study these two galaxies here, M33 and MGC91. So M33 is, you probably are all familiar with, it's one of our neighbors here in the local group. And the other galaxy, MGC91, is an adjunct spiral galaxy, not in the local group, but not that far away. It's actually pretty close to us. And the idea is to use photometric data to study the planetary nebula population of M33, to study their colors, and spectroscopic data of MGC91 to study the kinematics of the planetary nebula population. And we can see what we can infer about the galaxy. Okay, so I'm going to talk more about M33, the first part of my master's project, because it is complete now and being published. And we are currently working on MGC891. But at the end, I'm going to share a little bit about it as well, a couple of slides that we are presenting, and our next steps. Okay, so the main question that we want to explore here with M33 is whether J-PLUS photometry can effectively trace the planetary nebula population of M33. But more than that, if these new multi-band photometric surveys combining broad and narrow band can be a good tool to study extragalactic planetary nebulae. Okay, so first let's start with planetary nebulae. What are they? Why do we care about them? So they are late stages of stellar evolution associated with stars of low and intermediate masses, approximately between 0.8 to 8 solar masses. And this phase occurs when the star is at the end of its life, and it's exhausted. It has exhausted all the fuel for nuclear fusion, and it has passed through a lot of instabilities. And the result is that the outer layers of the stars are expelled, forming this envelope of gas that you can see here, that is ionized by the ultraviolet radiation of the core of the star that is now expelled. And this marks the beginning of the planetary nebula phase. This is actually a very short phase if we compare to the whole life of the star. It lasts approximately approximately 20,000 years, and the whole life of these stars can reach billions of years. Okay, but why do we care about them? They are excellent storytellers, if you will, about the interstellar medium and the chemical evolution of the galaxy, because they reveal information about the time and the place where the star was born millions and even billions of years ago. So, but more than that, they are not only tellers, but they also contribute to the chemical evolution of the galaxy, because they spread in the interstellar medium all of these elements that have been developed in the interior of the star during its lifetime. And more than that, they can be used, as we're going to see at the end of the presentation, they can be used as tracers of the old stellar population kinematics as well. So here we have two planetary nebulae that are very famous, that you're probably familiar with. The first one, MGC 6543, that's also popularly known as the Cat's Eye Nebula, because it has this peculiar morphology that I'm not even going to get into that in this work. And the other one is the Helix Nebula, popularly known, but it's MGC 7293. And they are very famous and characteristic planetary nebulae. Here we have an HR diagram showing the evolution of a star with two solar masses, just as an example. So we can see more or less where this planetary nebula phase happens and with what conditions. And in the right, we have this spectrum that is to show just the main and characteristic emission lines of planetary nebulae. This is one planetary nebula that we confirmed in my undergraduate project, where we selected planetary nebula candidates and spectroscopically confirmed them. So we can see, for example, H alpha, the nitrogen lines, O3, H beta, and other characteristic emission lines of planetary nebulae. Okay, so J plus, I'm not going to spend much time here. Probably most of you know more about it than me, but it is a photometric survey that we use in this work, covering it covers the northern sky, and we can see here its filter system. Because of its filter system, it has been extensively used to search for and study H alpha emitters, for example. And we can see here the 5 broadest ESS bands and the narrow bands, and I plotted on top of that spectrum of a planetary nebula that we previously confirmed in another work. And yeah, we're going to use J+ data to do that. So first we start gathering the planetary nebula population of M33 from these previous works. We end up with 143 spectroscopically confirmed planetary nebulae that you can see here in red. But cross-matching this with J+, we could only find 13 of them in the catalog. There are the yellow squares. Okay, so of these 143, we have only 13 of them. So we decided to, actually, let's analyze these 13 first. Okay, so initially we thought, why these 13 planetary nebulae? Are they the brightest ones? What's behind this? So here we compare the H alpha flux, the log of the flux, and O3 magnitude. And we can see that, okay, they are actually a little bit, the ones that we recover are actually bright, but it's not clearly separated, and we miss a lot of planetary nebulae that are brighter, actually. So what's happening here? We saw that J+ performs the automatic extraction with the R band, which it has H alpha, but it's not ideally for planetary nebulae because we have no continuum with planetary nebulae, very low continuum. So we decided to perform the extraction ourselves to try to recover more planetary nebulae. So here we have the 3 field of views we use of J+ to cover the galaxy. I'm showing here H alpha image, but we did that for the 12 filters and the 3 field of view. So we run SExtractor 36 images. And sorry. And we also test a lot of different parameters to optimize this extraction to identify planetary nebulae. And we tested different detection images as well. So in this first work, we present the results of the use of H alpha image as detection image. But I also did some tests with stack images. And even though we were recovering less planetary nebulae, we were recovering a few different ones. So it's not just a matter of more or less, but different planetary nebulae. So this is something that can be explored in the future, like what type of planetary nebulae we are recovering with different detection images, and also to increase the number. I think it was 9 more planetary nebulae or something like that with the few tests that I did. But in this first work, we are presenting the result with H alpha image as detection image, which gives us 98 of the non-planetary nebulae. So instead of only 13 planetary nebulae that we had before in the catalog, now we have 98 to do this analysis. Okay, but here we have the 143 non-planetary nebulae in M33. In yellow again, we have the 13 that were already in the catalog. In blue, the 98 that we were able to recover with our extraction, and in red, the 45 missing. Why are we missing these 45 planetary nebulae? So again, here we compare flux and O3 magnitude, and we can see that, well, they are in fact fainter, these ones that we are not recovering, but we can still see some of them, for example, here and here in these brighter parts of the plot. So we believe that what's happening here is that they are in very crowded central regions of the galaxy, or they lie exactly on top of spiral arms and H2 regions, which can make the detection with SExtractor more challenging. Okay, so another thing that we did for this, because with SExtractor we have aperture photometry, which can be a little bit complicated when we have very crowded fields. So we also try to obtain PSF photometry. So we use the PSFEx, which is another software usually associated with SExtractor that builds the PSF model. So what we have here is all the extracted sources from those images that we use as an input to the PSFEx. And the PSFEx can either select the stars automatically to build the PSF model, or we can put them as an input to make sure that we are selecting good sources. So we decided to do that. We are ourselves selecting the stars. So we restrict ourselves to these regions of this parameter space of this plot, these red point-like sources, so we can avoid saturated objects, extended objects, and possible cosmic rays detections. We also applied a few extra criteria to guarantee that they are well measured point-like sources. So for example, limit in the error of the magnitude to make sure that we are using sources with magnitude well measured. Class star greater than 0.7 because class star close to 1 means point-like sources and close to 0 extended objects. And flags equal 0, that also means possible point sources. Okay, so PSFEx actually builds the PSF model, and then we rerun SExtractor with the PSF model to obtain PSF photometry as well, and aperture photometry. Okay, so with this photometric data available, this new photometric data available, we decided to analyze them on color diagrams that we have here. Sorry. Okay, so here we have all the extracted sources from those images, these gray clouds in the back. They are all the extracted sources from the field of views that we used. In red, we have the planetary nebula, and in blue, this one blue circle here represents one planetary nebula that, according to Tiardul and collaborators 2004, could belong to the halo of M33. And these black lines represent color criteria developed in a previous work from a collaborator with Cherry Soto and collaborators 2020 to search for galactic Milky Way halo planetary nebulae that we plot here just to maybe assess the possibility that some of these planetary nebulae might belong to the halo, or to see if these color criteria are actually selecting planetary nebulae even from the disk of M33 as well. So we have 5 planetary nebulae in yellow that meet the criteria of all diagrams, of all the 4 at the same time. And we decided to take a look into them. And also this purple, very dark purple, represents 16 sources of these extracted sources from those images that also meet the criteria of the 4 diagrams. So they could be potential planetary nebulae candidates, maybe. We decided to take a look at them as well. So these plots here just to show the location. It's not very good to see, but it's just the location of the objects that we are selecting with the color criteria in each diagram. And when we cross-match them, when we combine them, we have those 5 planetary nebulae in yellow that I told you before, that met the halo criteria, and the 16 extracted sources that also obey the criteria. You might be wondering why these possible candidates are constrained to the south of the galaxy. We wonder that too. And this made us look back here and see and ask ourselves what's going on in this field here, for example. And we also noted that when we use these 2 diagrams, these first 2 diagrams, that are the ones with the I band, we selected more sources in the south of the galaxy. So this made us revisit everything we have done. We couldn't find any mistake there, but we found this paper from Lomeli Nunes and collaborators 2025, very recent, where they have a very similar situation, and they did a very thorough analysis of the observational conditions and how they can impact the detection of the sources. And yes, they analyzed parameters like air mass, the background statistics, and they saw that these can be very much related to the detection of sources. But before concluding that this was the case here, I also investigated this region of the galaxy to see if I could find any interesting explanation for this. So I checked, a spoiler alert, most of them are actually H2 regions. They are the most common contaminant for planetary nebulae. So I checked a lot of papers about the H2 regions of M33 to see if they have a concentration in this region. I also checked papers on the H1 clouds around the galaxy to see if I could find anything interesting. We explored the connection between M33 to M31, the interaction. Nothing could gives us an interesting explanation of why this is happening. So just based on these diagrams, for example, these limitations here, and this over selection in the south compared to the north, we concluded it's just probably observational, difference in observational conditions. Okay, so these are the 5 planetary nebulae that met the criteria of all diagrams at the same time. And we decided to do a simple kinematic analysis of them. So here we have the velocity of the planetary nebulae minus the systemic velocity of the galaxy for all the planetary nebulae, all these red dots. And we plot here the planetary nebulae that, according to Ciardullo and collaborator, could belong to the halo of M33, but not according to our photometric analysis and the simple kinematic analysis that we do here. And the 5 planetary nebulae that pass the halo criteria, we only have kinematic information for 4 of them, these ones here. Because for the 143, 313 are very recent ones, and we couldn't find the kinematic information. One of them is one of these 5. So we have these 4 here. And according to this simple diagram, where we expected the halo objects would lie around here, showing very little rotation, only one of them could actually be associated with the halo of M33. Moving on to the 16 sources, as I told you before, most of them are H2 regions, and only one of them, we couldn't find anything in the literature that could be a possible planetary nebula candidate. We don't know. It's not part of this work to confirm that or deny that, but it's a possibility for the future. And especially looking at these SEGs, the planetary nebula SEGs and the H2 regions SEGs, it looks like it could be, maybe. So yeah, what can we conclude and discuss about this first part of the work? So we were able to successfully recover the photometric data, J-PLUS data, for 98 previously known planetary nebulae instead of only 13 in the catalog, which shows that despite the fact that J-PLUS was not specifically optimized for planetary nebulae studies or detection, it can be a good tool to study these objects, to search for them, to trace them, if we perform the extraction ourselves, if we manipulate the images with this goal of finding planetary nebulae. Another interesting thing that we found was the fact that different detection images reveal different planetary nebulae. So this is something that our group wants to explore in the future. Like we have 4, or maybe depends on what classification you use to divide the planetary nebulae population. And we want to see if a specific band, a specific image, a specific filter selects a specific type of planetary nebulae or something like that. So this can be explored in the future, and also to increase the sample of 98 to a higher number. In the diagnostic color diagrams, we can see that many planetary nebulae of M33 have similar colors to galactic halo planetary nebulae, especially in this diagram here, of 70% of them are in this region. And this is actually expected because the chemical abundances of the planetary nebulae in M33 should better compare to the Milky Way halo than with the high metallicity disk. So when we apply this color criteria, we actually expect to select a lot of disk planetary nebulae in M33 as well. When we combine this photometric criteria, this photometric analysis with the kinematic analysis, we saw that only one of these planetary nebulae could actually be associated with M33 halo. And this also makes sense because there are previous works showing that the stellar halo of M33 contributes very little to the galaxy luminosity, so we don't expect to find much there. And therefore, we expect the bulk of the planetary nebula population of M33 belongs to the disk. And investigating those 16 sources, we saw that these diagrams and these color criteria might be a good way actually to identify H-alpha emitters, but not necessarily planetary nebulae. And this highlights the necessity of combining this color criteria with additional criteria, for example, regarding the size of these objects. We do this analysis of the fluid half maximum of them, for example. If we apply a limit in the fluid half maximum for these 16 sources based on the fluid half maximum of the planetary nebulae, that is what we have here in this first plot, only one of these 16 sources would remain a possible candidate. So this shows the importance of combining additional criteria, especially regarding the size, to try to eliminate these H2 regions. In the thesis, actually, we discussed a lot about additional criteria that could be developed for future work, because we know that it's not the goal of this work to select planetary nebulae candidates, but it is to test J-PLUS strengths and limitations to study this type of objects. But future works could be done based on the data we have been published now, and to search for extragalactic planetary nebulae because the nearby galaxies lack these catalogs of planetary nebulae. And we discussed possible criteria that could be developed based on the SEGs, for example, because we have these J-PLUS SEGs for all the extracted sources, for planetary nebulae, for H2 region, globular clusters, and all objects that we can extract from those images. So we can analyze them and develop color criteria, or even a difference in magnitude, or any criteria that could be useful to try to separate planetary nebulae from contaminants. But talking about the future, J-PASS would probably be a better survey for this type of work, because it has, if I remember correctly, 56 narrowband filters, ranging from 3,800 or something until almost 10,000. So almost like low resolution spectroscopy. And a lot of these narrowband filters lie on top of very important emission lines for planetary nebulae. The one that I find most exciting is the helium-2 line, because we don't expect H2 regions to reach such high ionization. So this could be a good tool to photometrically separate planetary nebulae from H2 regions that are the most common contaminants when we look for planetary nebulae. Okay, so if I have time, and I believe I do, right?
Yeah.
Okay.
Plenty of it.
I'm going to talk about the second part of the project. That is what I'm currently working on at the moment about NGC A91. As I said before, here we use spectroscopic data to study the properties of the galaxy through the kinematics of the planetary nebula. So the main question we want to explore is what properties of the galaxy we can infer through the planetary nebula kinematics. So for this project, we use data from the Planetary Nebula Spectrograph. That is a spectrograph that we can see here how it operates, but it has a counter-dispersed imaging technique, which allows us to obtain the velocity and the position of these objects at the same time. And it is equipped with an O3 filter. So the planetary nebulae will appear as dots like this, as point sources like this, because of the emission line and the low continuum, while stars will have this more extended appearance because of the high continuum. So it's a good way to identify and extract these sources. For example, here we have a normal conventional O3 image of a specific field. I think 1031 here, if I don't remember correctly. And here we have the comparison of the same field with the PN.S. So the left arm and the right arm of the PN.S. So we can see that the stars will have this more extended appearance, while the planetary nebulae will look like dots, and they are deviated from the left and to the right, which allows us to obtain the position and therefore the velocity of these objects. Okay, so here we have 6 different galaxies, because the PN.S actually observed a lot of galaxies, spiral, spherical, and elliptical galaxies as well. And this NGC A91 is the only one that was left behind. So I'm now finishing this work almost 20 years later. And the premise of this work is that we can trace the stellar light with the planetary nebula. So what we can see here in these 6 galaxies are the surface brightness of the stellar population. We probably can't see that, but these are diamonds. And for some of them, they don't reach such high radius, but we can see these diamonds represent the stellar surface brightness profile. And the blue and green curves are just a extrapolation of that with successive profiles with different indices. And the black dots represent the planetary nebulae density, which means the corrected number of the planetary nebulae in that region, in the area. And we can see that they behave quite well, and they apparently trace very well the stellar line of the galaxy. Okay, so we have the catalog extracted with 118 planetary nebulae, and we need to work on the completeness of this data. So what we do first is that we insert a lot of artificial point sources in these images with magnitudes brighter than an 80, that we call it. It's the magnitude for which 80% of the planetary nebulae are recovered. So when we do this, we make sure that any loss in detection can be associated with contamination from the galaxy light or those stellar trails that I showed you before. So we populate these images with these artificial sources, and then we extract them to see what fraction of them we are recovering. That is what we have in this plot, the recovered fraction and the distance from the center of the galaxy. So we divide our planetary nebula in beams in different regions, and we multiply the number of the planetary nebulae by the correction factor, that is the inverse of the recovered fraction for those specific beams. Okay, so doing that with the correction, the completeness correction, we try to build those same plots that I showed you before here. So what we have here in blue is the surface brightness profile, the stellar surface brightness profile. In green, we have the static fit for the bulge component. In orange, the disk, and this black dashed line represents the combination of those two. And here is just to show you, we ran these Gaussian models just to show you that the model disk plus bulge actually works better. It's not that good yet, but we are still working on that. But it's just to show that the two component disk plus bulge represents better what we have in this galaxy. So it's these black lines, and the black dots represent the planetary nebula density. And we can see that they also trace quite well the surface brightness of the galaxy. Okay, so just to show you a little bit of what I'm doing at the moment. I don't have that many results yet. Actually, yeah, I just have that for now and a few more plots that I'm analyzing. But we have here all the planetary nebulae, and we can see that they extend quite further from the thin disk. This plot here, sorry, it's not very pretty because it's not going on like this, it's just for our analysis, but it's just to show you that the H2 regions, for example, as we expected, are very constrained to the thin disk, while the planetary nebulae expand way further. Okay, so we have this velocity map, and we have also this plot about regarding the velocity of the galaxy and the distance from the center. Here we folded the one side of the galaxy, so we have all of the distance from the two sides of the galaxy represented in only one plot. And we have this velocity, and these dashed curves represent the height from the plane. So we can see, for example, that we're increasing this height to have a lower rotational velocity here. But yeah, we can already see a few interesting features. For example, maybe we can investigate this negative part of the plot and these red dots in this left region of the plot that could be associated with a halo population. So this is what I'm currently working at the moment, investigating these plots and a few more. But what we want to do is what we're doing now, actually the first two maybe, is assess the possibility that some of these planetary nebulae belong to the halo of NGC91 based on the kinematics. Investigate if in some cases just velocity dispersion is still associated to the halo, to the disk, or if they are halo-like population. And we also want to study the asymmetrical distribution of the planetary nebula in this galaxy, see if it is associated maybe with stellar streams or any other interaction with other galaxies. And investigate the origin of the thick disk, if it is just an extension of the thin disk, or if it is associated with a merger event. And we also want to compare the planetary nebula distribution with H1 distribution to see what we can find. Of course, not all of this will be done by my master's thesis defense, that is next month, But we plan to finish in the months that I'll have between the master's and the PhD to publish all of this in the paper. And now, yes, now that's it. Thank you for your attention.
Thank you very much. Very, very nice talk. Question? Sandra?
I actually have several, but I will just, so let's start with one on the first part of your presentation. When you speak about the velocities of the planetary nebulae in with J-PLUS, those are velocities that you derive, right? Those are velocities that you derive from the spectra, that or from the SED, or how?
No, I didn't derive them. These are published and in Terdulan collaborators 2004.
Okay.
They
So
published
these
the
are-
velocity because they observed them. They
Okay.
have the spectra.
All right.
Derived from the spectra, but it's not done by me.
Okay. If I may,
Yeah, yeah. Go ahead.
skipping on the, I'm sorry, I'm skipping. I'm quite familiar with J++. Plus, I'm co-author of the papers. I'm quite familiar with the whole thing. So on the PN.S part, how do you separate? Because you comment that you have both planetary nebulae and H2 regions. How do you tell which is which?
You basically have to reach common sense between all the members in the collaboration, but it's visual inspection and also the trying to estimate the size of these sources.
Okay.
But I haven't done that. They did the Planetary Nebula. So the PN.S group did the extraction of the catalog. I have the catalog with the Planetary Nebulae and the H2 regions, but the H2 regions will also appear more or less like this.
Okay.
And they do based on common sense between them, agreement between them, but based on the size of the sources, for example, the width maximum and visual inspection. But it is something not quite certain, because, for example, when I got this data, they were all together and they were marked as planetary nebulae in possible H2 regions. So we can see that it's not very common, it's not very easy to separate them. It's easy to detect planetary nebulae instead of stars, for example.
Right.
But the H2 regions, I would say it's a weak point maybe. But it's something that has been done in all of these, for all these galaxies, so they can do it.
My very last question as well, Stone. Sounds like I'm a tribunal of PhD. When you show the rotation curve that you derive, there, so the lower right plot, I guess at least to the older ones of us, to me reminded me of the Vera Rubin plot of the rotation curve. So I have two questions here. The easy question is this what you expected to see? And the difficult question is, what is the error bar on each point and how much the scatter is actually representative, or you were expecting that scatter?
Okay, I would say that it is more or less what we expect. This is actually a very recent plot that I haven't even shown my supervisors yet. I'm going to show tomorrow, but they saw this one. But yeah, I would say this based on previous work with the PN.S. I would say that this is more or less what we expected. I was actually trying to reproduce the plots that they had done before with other galaxies. And regarding the error bars, yes, I haven't plotted them, but I have the error in the velocity. They exist. They're not very small, but for example, for these 118 planetary nebulae, we actually had 16 of them. There are presented because the NGC91 was observed in two arms, two images. So we have the right side of the galaxy and the left side of the galaxy. So I worked with these two images. And when I joined them, I saw that 16 planetary nebulae in the center were repeated from these three images. And I compared their velocity, for example. And they have a difference of maybe reaching 40 kilometers per second. I mean, the highest difference. So I know that they do have a difference just based on one image to the other. And there's a few analysis that we did based on that as well. But yeah, I should plot them.
No, so it was just my curiosity if the error bars were like 10 kilometers a second or 100 kilometers a second.
No, not 100 actually, but more like 10.
Okay, cool.
More questions?
Yeah, really nice talk. Thank you. So my question is more because I'm really ignorant about planetary nebula, and you said that it's very hard to separate them from H2 regions. So my question is there not any specific line or something that you can use in the SEDs or line ratios or something? I'm asking because I don't know.
Yeah.
So,
Well, this is actually one thing that we conclude because with J-PLUS, I would say it's difficult.
yeah.
But with J-PLUS, this could be explored with this helium line because they have very similar H-alpha emission or 3 emission, but they lack these very high ionization lines because they usually don't reach these high ionization stages. But with J-PLUS, this is all we can do. But actually, until now, I would say that we definitely need spectroscopy to confirm planetary nebulae nature. But there's much more that we can do now with photometry alone. For example, with J-PLUS, I would say that if we actually have a quite good way to separate this helium-2 line, would be half of the way to confirm maybe a planetary nebula just with photometry. But yeah, that's the thing.
Just a comment on that. Is there a particular ratio, helium to H beta or something like that, that you use to separate the populations?
I'm not sure if I think that's not a constant value for a planetary nebulae. But maybe if they are higher than some limits, maybe we could say that it's probably a planetary nebula.
Okay.
I was just going to ask, something about, like for AGN, we have AGN and galaxy, there is sometimes a PVD diagram that you plot different emission line ratios between, say, H alpha and hydrogen, whatever.
Yes.
And then you can see the differences, like if it's actually a planetary nebula, just a helium rich.
Yeah, we have also these radios for the nitrogen lines, for example. They have to be one of them, the red one, has to be 3 times the left one around H alpha. We have these actually the H alpha to H beta. We also have this 2.7 radio, but it could be influenced by the extinction. So it's actually a possible way to characterize, but not a definite way. But yeah, this is something we can explore and we have been exploring.
Yeah, to add to that, what about luminosity?
About planetary nebulae in which?
Yeah, I mean, like, is there some kind of cap, like limit you say, if this is above this limit?
Yeah, actually, when we compare, for example, here I put the planetary nebulae, and the H2 regions here, we can see that the planetary nebulae are usually fainter, for example, but there are high excitation planetary nebulae that could mimic these H2 regions or vice versa, or very compact H2 regions that could, and these compact H2 regions are the most pain contaminants because we can even discard them by the size sometimes, so it's a problem. But yeah, they do have this difference in general, but there are few particular cases of planetary nebulae or particular cases of H2 regions that they can overlap.
There's some kind of rough magnitude difference between, you say?
Not that I have by my head, because it also depends on what telescope, what we are using to observe, and the distance as well. But I don't know if there is a common value, a common difference between them. But yeah,
Maybe equivalent width to be more effective to distinguish them, no? Because the planetary nebulae they have very strong lines,
yes,
but very generally much longer continuum. But still there, you will have some H2 regions that enter in the, that can have very high equivalent width values.
yes, yeah, of course, because of the star. Yeah, that's true.
Thank you for the talk. It was very clear, and congratulations for the work. I have just a few technical comments. Can you show again in the first part of the talk the access planetary nebulae that you find in M33? This one.
So this one.
Yeah, that will work. So, well, first of all, all the process that you follow to, I mean, of course, J-PLUS is not intended to, doesn't work well in crowded regions, so all the process that you follow makes all sense. It's natural to use other detection image for detecting the sources of your interest, and then make actually the photometry on that. So that's my first comment. But it looks to me that if you see, actually, can you go back to see in more detail? That's it. No, the next one. So it seems to me like there are an excess of detections that correlates with the borders of the tides.
But for those 16, we zoom in, and that's not actually the case. It's not very on the border.
That's just to mention that there is some correlation, not for all the sources, because there are others that are not actually in the line of the border of the tile. And then the explanation could be, I don't know, maybe different depths of the image that you are more. I really don't know, but could be a possibility. And so I just wanted to comment that. And an extra comment for the future is that you know that in J-PLUS and J-PLUS we have, well, it's a cosmological survey initially, so it is not well tailored for very large sources, nearby sources like galaxies, extended galaxies. But we plan to make for those particular objects like M33 to make a devoted tile that is not going to have borders centered to that, and maybe actually make it larger or adapt the size of the tile for the particular object, because they are just a few, and maybe these problems will be less in the future with that.
And actually,
a single observation.
And actually, there's a postdoc here working on detection of objects in extended sources. Like Eduardo is a Brazilian guy, you may or may not know him, and he's working on this kind of extended source. I may introduce you to him.
Okay, thank you.
More questions?
If I may, just so this is your master project, and when are you supposed to defend the master?
May, the end of May.
And what happens to your life afterwards?
I'm looking for a PhD position.
Oh, how spontaneous! It was not planned at all.
I forgot to mention that. Yeah, I was trying to see first if this would be a good propaganda or not.
Patient is also.
Yeah, thanks for reminding me.
Okay, if there are no more questions, let's take this. Giovanna again. You're pleased.
One. Sí. ¿Tú estás aquí la semana que viene?
Sí.
¿Te puedo pasar el marrón de